All right, in this video, we're going to go through the entire Semester 2 study guide. So we're going to start with Unit 5, which covered reactions. So first question says, predict the products of the following reactions, balance the reaction, and determine the type of reaction. Okay, so working with reactions, the first thing that we're going to do is we are going to write out all of the charges. Okay, so for our first one here, we have copper. We have bromine, we have aluminum, and chlorine. So on our periodic table, bromine is in group 7 and has a charge of -1. Chlorine is also in group 7 and has a charge of -1. Aluminum is in group 3 and has a charge of +3. And we have to look, copper is a transition metal, we have to look at what it's attached to. So we have 2 bromines. Each bromine is -1, and there's 2 of them. So that's a total of -2. So copper has to be a +2 to make that work. All right, this is going to be a double replacement reaction. So we have 2 compounds here. So copper is going to combine with chlorine. So copper and chlorine, we need 2 of those to balance out with copper's +2 charge. And then we have aluminum, and we need 3 bromines to balance with our aluminum. All right. And then as far as balancing goes, I'm going to do this first one with a table. So I'm just going to kind of do this up here. So let's see, we've got copper, we have bromine, aluminum, and chlorine. So I'm going to make a table that has everything on it. And let's go through and let's count up what we have. So we have, on the left side, we have 1 copper, 2 bromines, we have 1 aluminum, 3 chlorines. On the right side, we have 1 copper, 2 chlorines, 1 aluminum, and 3 bromines. So our coppers are balanced. Bromine is not. And we have a 2 and a 3. So we're going to need a multiple here. The least common multiple is 6. So on the left side, let's put a 3 here. 3 times 2 is 6. And let's not forget about the copper. Okay, so 3 times 1 makes this a 3. On the right side, to get our 6 bromines, we're going to need to put a 2 here. 2 times the 1 aluminum makes this a 2. 2 times 3 makes this a 6. Okay, so we balanced bromine, but we totally just messed up our coppers. So we need 3 coppers on the right side. So let's put a 3 here. 3 times 1 makes this a 3. 3 times 2 makes this a 6. Okay, so we only need one more thing, it looks like, to balance this. If I put a 2 here, 2 times 1 is 2. 2 times 3 is 6. Okay, and as I mentioned earlier, this is a double replacement. Also known as a double displacement reaction. Okay, number 2. Same thing. Let's start by doing our ions. So we have, let's see, sodium, Na. We have iodine, and we have bromine. Sodium is +1. Iodine is -1. Bromine is -1. This is going to be a single replacement reaction. So sodium is going to match up with bromine here. They are both magnitude 1, so we don't need to have any subscripts here for this. So it's just going to be Na, Br. And then iodine is one of those that's on our polyatomic list. So the saying that I use is I have, oops, why is it making lines? I have no bright or clever friends. Okay, so those are diatomics. Anything that's by itself, okay, that's on that list, I have no bright or clever friends, has to be with a buddy. So I need 2, since iodine is on that list right here. I need 2 iodines. This one's relatively easy to balance. So I know that I have 2 iodines on the right side, so I'm going to need 2 on the left. Okay, so if I put a 2 there, that 2 goes to the sodium and the iodine. And to balance that out, I'm going to throw a 2 here. Okay, the 2 will clear out my 2 sodiums, and then I have 2 bromines, and I have 2 bromines. Okay, that one was relatively easy. You could make a table every time, just to be sure, but that one was able to just kind of eyeball. All right, the third one is a little harder because it's all written out in words. It says 2 moles of sodium phosphate react with 3 moles of calcium chloride. So 2 moles of sodium phosphate. Okay, so phosphate is on our table of polyatomics. So in your resource packet, if you go to the table, of course it's like the last page, the table of polyatomic ions, okay, phosphate is right here, PO4, with a -3 charge. So 2 moles of sodium phosphate. So I'm got a lot going on here. Why don't I erase this since we're done with this? Just so we have some more room to work. Okay, so sodium phosphate, so Na, and then phosphate is PO4, and it's a -3 charge. Sodium is a +1 charge. Okay, and then calcium chloride, so Ca, Cl. Ca is +2, Cl is -1. Okay, this will be a double replacement reaction. Oh, you know what? I just realized I forgot to write this one out. So this one that we just did was a single replacement reaction. Because we had something by itself. It was the bromine by itself, and then we had a compound, sodium iodide. Okay, back to number 3. So 2 moles of sodium phosphate, so I would write that out like this. So sodium phosphate, oof. So I'm going to need 3 sodiums to balance out with that -3 charge. So Na3PO4. Okay, and then we have calcium chloride. So I'm going to need 2 chlorines. Okay, and then sodium and chlorine are going to combine. So NaCl. And then calcium and phosphate. We're going to need 3 calciums and 2 phosphates because we're going to need a least common multiple of 6 here. Okay, before I forget, this is a double replacement reaction. Double replacement reaction. Okay, this one is going to be a little trickier to balance, so I have enough room. I'm going to erase my work up here from the first problem, so I have some room to balance this. All right, and I'm going to work up here, so let me split this in half. So we have sodium, Na. We have phosphate, PO4. We have calcium and chlorine. Okay, let's count up what we have. So 3 sodiums, 1 phosphate, 1 calcium, 2 chlorines. 1 sodium, 1 chlorine, 3 calciums, and 2 phosphates. Okay, so let's see here. Sodium's not balanced, so let's start with that. Let's put a 3 on the right side. So that becomes 3. And then 3 times 1 makes this a 3. Okay. Phosphates, we've got 2 on the right, we have none on the left, so let's put a 2 here. So 2 times 3 makes this a 6. 2 times 1 makes this a 2. So now, and this happens sometimes when you balance, if you look at my sodiums, I unbalanced them. So 3 wasn't the right number to put there. We need to make it a 6. So let's go back and let's change this to a 6. So now 6 times 1 makes this a 6. 6 times 1 makes this a 6. Okay, so let's look at our calciums aren't balanced. So we've got 3 on the right, none on the left. So let's put a 3 here. 3 times 1 makes this a 3. 3 times 2 makes this a 6. And would you look at that? We are all balanced here. All right, moving down to number 2. For each of the following, use an activity series to determine whether the reaction would take place or not. If the reaction takes place, write the formulas for the products of the reaction and balance it. If no reaction takes place, write NR. All right, so activity series. I just so happen to have some right here. Okay, I think this is actually the one that we used in class. So here's an activity series. Basically what happens with the activity series is anything on the activity series, if it is above something, that means it can replace it. If it's below it, it will not work. So for example, zinc. Zinc is right here. Okay, anything above zinc, zinc cannot knock out. Okay, so like aluminum. If zinc wanted to replace aluminum, zinc isn't higher on the activity series, so zinc would not be able to replace aluminum in a single replacement reaction. Okay, zinc could replace iron in a single replacement reaction because zinc is higher than iron on the activity series. Okay, so with that in mind, let's take a look at the first one. Oh, look at this. We've got lithium and iron. Okay, so let's go back to the activity series. So lithium is at the very top. Iron is way down here. So lithium wants to come in and knock out iron. Okay, totally fine because lithium is higher than iron on the activity series. Okay, so this reaction will take place. So let's go ahead and write out the formula. So we've got lithium, we have iron, and we have NO3. And we actually have 3 of them. Okay, so NO3 is -1. There's 3 of them, so that means our iron has to be +3. And lithium is +1. All right. So lithium will swap out with iron. Lithium's going to bond with our NO3. So we're going to end up with iron by itself. Just solid metal iron. Oops. Solid metal. And let's see, we're going to have LiNO3. Okay, and then this will be aqueous. Okay, to balance this one's pretty easy to balance. So lithiums, we have 1 and 1. Let's see, irons, we have 1 and 1. Our nitrates, if you look, we have 3 on the left, and we only have 1 on the right. Okay, so we're going to need to put a 3 here. Our irons were balanced, but since we put a 3 there, we're going to need to put a 3 on this side to balance it out. Okay, now we're good. All right. B says we've got AU and we have HCl. So let's go to our activity series. So AU is gold. If you look on the activity series, gold is at the very bottom. Okay, and chlorine. Where's chlorine? Oh no, sorry. We're looking at hydrogen. Hydrogen is right here. Okay, so gold is way below hydrogen. So gold won't knock out hydrogen. So in this case, we are going to have no reaction. Okay. All right, Number 3 says, write the molecular equation and the net ionic equation for the following reactions. Identify any spectator ions. Okay, we're going to need a little bit more room for this. So I am going to make a new page here. And okay, so we have a new page. These can get a little messy, so I want to make sure that we have enough room so that you can see what's going on. All right, so let me go ahead and rewrite our equation. Okay, so we've got for A, we have, let's see, we had Fe2, SO4, 3 aqueous. We had KOH, aqueous. Then we had FeOH3, solid. And then finally, we had K2SO4, aqueous. Okay, so it asks us to write the molecular equation, the net ionic equation, and then to identify spectator ions. Okay, so molecular equation is basically just a balanced chemical reaction. So here, I bet you we're not balanced. So let's start by balancing this. So we've got, let's see, we've got iron, we have SO4, we have potassium, and we have hydroxide. All right. So let's see, we have 2, 3, 1 and 1, 1, 1, 2, 3. All right. So irons aren't balanced, so let's put a 2 here. So this becomes 2, and our OHs become 6. Okay. Our SO4s aren't balanced, so let's put a 3 here. So that'll make this, let's see, 3 times 2 is this is going to be a 6. 3 times 1 makes this a 3. And, oh, this is easy. Let's just throw a 6 there. Okay, great. So that's our molecular equation. The next thing that we're going to do is we are going to split every single aqueous compound into its ions. Okay, so this is the molecular. It's very important that it's balanced. And the total ionic is going to be everything that is aqueous split into its ions. Anything that has a subscript, that subscript will get pulled out in front. So let's do this. So we have 2 Fe, okay, iron. Iron is +3. And we're going to carry over the state of matter, so it's going to be aqueous. Okay, and then we have our SO4. Again, we have a 3 in front, so it'll be 3 SO4 minus 2, aqueous. The 6 is going to distribute to both pieces, so we'll have 6 potassiums. We'll have 6 hydroxides. And then on the other side, we'll have 2 irons. Oh, wait a minute. Oh, I just made a rookie mistake. So, if you have something that's a solid, we do not split it up into its ions. Okay, that's only for aqueous. I believe I said that, but let's go ahead and rewrite this. So, Fe, OH3, solid. Okay, and then I have one more here. So that 3 is going to distribute, so it'll be 6 potassiums. And potassium is +1. And then 3 SO4. SO4 is -2, aqueous. Okay. Anything that exists on both sides we can cross off. So our SO4 is on both sides. Let's go ahead and cross that off. And what else? Is there anything else we can cross off? Potassium exists on both sides. Let's go ahead and cross that off. And I believe that is it. Okay, so that's our total ionic. Our net ionic is anything left over? So we have 2 irons. We have 6 OH minus, and that is going to yield 2 irons. Okay, our spectators are anything we crossed off. That were on both sides. They weren't involved in the reaction. So our spectators were 3, actually I don't even need the number. So our spectator ions were SO4 minus 2, and we also crossed off our potassium. Okay, those are the spectators. All right, so we have another one. So if we go back to the study guide here, number 3B is also the same thing. So I'm going to go down and let's see, do I have enough room? Let's just do another page. Don't have to worry about wasting paper on the computer. Okay, so I'm going to rewrite the problem. So B was, let's see, we had MgCl2 aqueous. We had Li2CO3 aqueous. We have MgCO3 solid, and we had LiCl aqueous. Okay, so that is our molecular, and we do need to balance this. So let's do that first. So magnesium, chlorine, lithium, and CO3. Okay, so let's see. 1, 2, 2, 1, 1, 1, 1, 1. Oh. Wow. Look how lucky we are this time. All we need is a 2 here. And we're balanced. So that's our molecular. Next is our total ionic. Okay, so we're going to split anything that's aqueous up. So we'll have, let's see, Mg plus 2 aqueous. We'll have, so watch this 2 here, 2Cl minus aqueous. We're going to have, again, we have a 2 here, so 2 lithium. Lithium is plus 1. And then CO3, that's a minus 2 aqueous. Not going to make the same mistake twice. We got a solid here. Why is it not circling? There we go. We have a solid, so I'm going to leave that alone. And then we have 2 lithiums. Oh, just couldn't quite fit. And then we have 2 chlorines. Okay, that's our total ionic. We look for anything that exists on both sides to cross off. So that's going to be our chlorines, our lithiums, and that's it. Next is our net ionic. That's anything we didn't cross off. And then our spectators are anything we did cross off. That was our chlorine and our lithium. Okay, those are our 2 net ionics. So let's go back up. And where did we leave off? Okay, number 4. Determine the oxidation number for each element. All right, so for the first one here, we have a couple rules. So for this first one here, we're a little tight on space here. So for our first one here, we have hydrogen, we have sulfur, and we have oxygen. We have 2 hydrogens, we have 1 sulfur, and we have 4 oxygens. All right, now oxidation numbers. Hydrogen is going to be +1. Sulfur we don't have a rule for, so we'll just put an X there. And then oxidation number is -2. Okay, so let's see, this will be +2 when we multiply. This will be X, and 4 times -2 will be -8. We know that we want this to add up to 0. So for this to add up to 0, sulfur needs to be, this right here needs to be a +6. Okay, so hydrogen will be +1. Sulfur will be, what do we say, +6. And then oxygen -2. All right, this is going to get a little too crowded, so I'm going to go ahead and erase this. All right, the next one, we have BaCl, barium chloride. So same thing. We have Ba. We have Cl. All right, we have 1 barium. We have 2 chlorines. Barium is +2. And chlorine is -1. Whoops. Okay, chlorine is in group 7. Okay, so this will be +2. This will be -2. We add those up and they equal 0. Okay, so that's good. So we've got barium. Barium is +2. And chlorine is going to be -1. All right, we got one more. I recommend for the oxidation numbers just looking over, because there are a couple rules, and then anything you don't have a rule for, you kind of have to go back and solve. All right, so our last one, we have magnesium, and we have NO3. So we have nitrogen, and we have oxygen. And we want this to equal 0. All right, so magnesium, there's 1. Nitrogen, there are 3. And nope, I'm sorry. Let me go back. Nitrogen, we only have 2 of those. Okay, so the 2 is going to distribute, so 2. And then oxygen, we have 6 of those. So we have 3 inside the parentheses, and the 2 on the outside makes that a 6. Magnesium's +1. +2, sorry. Ugh. +2. Nitrogen, we don't have a rule for. Oxygen is -2. So this will be +2. This will be 2 times X, and then this will be -12. We want it to add up to 0. Okay, so we have +2 and -12, so that equals -10. And then, let's see, we have 2x. So we need to solve for x, divide both sides by 2. X is going to equal +5. Okay, so our numbers, let's see, we had magnesium, +2, nitrogen, +5, oxygen, -2. Okay, number 5 talks about galvanic cells. We actually skipped that this year, so let's go ahead and just cross that off. All right, number 6 asks us to classify the following reactions. All right, so for the first one here, we have, let's see, we have something by itself, we have something by itself, and it goes to a compound. So that is synthesis. And it asks us to identify if it's a redox reaction or not. So let's zoom in just a tad here so we can make this a little bigger. Okay, there we go. So let's assign oxidation numbers. Hydrogen is 0, nitrogen is 0, and NH3. Okay, so we have a compound here. We want it to add up to 0, so this is going to be -3 because hydrogen is +1. So we go from 0 to -3, and we go from 0 to +1. This is totally a redox reaction. All right. The next one. Okay, so we have compound, compound, and compound, compound. Copper ends up going with chlorine, and bromine ends up going with aluminum here. This is a double replacement or double displacement reaction. Okay, and let's go through and assign oxidation numbers. Okay, so bromine group 7 -1. There's 2 of them, so copper has to be +2. Aluminum +3. Chlorine -1. And on the other side, same thing. Let's see, chlorine is -1. This is going to be +2. Aluminum is +3. And bromine is -1. Okay, so copper goes from +2 to +2. Bromine, -1 to -1. Aluminum, +3, +3. Chlorine, -1, -1. None of our numbers change. This is not a redox reaction. Okay, next. Now this might look like maybe a single replacement or double replacement, but look here, we've got oxygen, we have carbon dioxide, and we have water. This is a combustion reaction. Okay, let's assign oxidation numbers. All right, carbon is +1. So I said carbon. Hydrogen is +1. So let's see, this would have to be -3. Oxygen, it's by itself 0. Okay, oxygen here, -2. 2 times -2 is +4. And let's see, hydrogen's +1, and this is going to be -2. Okay, carbon goes from -3 to +4. Let's see, hydrogen doesn't change. Oxygen goes from 0 to -2. So we've got a change here. This is a redox reaction. Okay, D. D, we have a compound, and then we have something by itself. On the other side, we have a compound and something by itself. This is a single replacement. Okay, let's go through and assign oxidation numbers. So let's see. Oxygen's -2. Nitrogen, let's see, Ag, this is going to be +1, +3. Did I do that right? No, that's not +3. That's going to be +5. So -2 times 3 is 6. There we go. So now those cancel out. Nickels by itself, it's going to be 0. On the other side, let's see, this is -2. So that means, let's see, this would have to be +5, and then this is going to be +2. All right, this is by itself, it's going to be 0. Okay, so let's see. Nickel goes from 0 to +2. Nitrogen doesn't change. Ag goes from +1 to 0. That's definitely a redox reaction. All right, here. E. By itself. Okay, oxygen's -2. This is going to have to be +1. To balance that out, we go from -2 to 0, and we go from 1 to 0. This is definitely a redox reaction. And we're going from a compound and breaking into two smaller pieces. This is decomposition. Okay. Calculate the molar mass of Al2SO4. All right, so when we calculate molar mass, we're going to need to go to our periodic table and look everything up. Okay, so here is my periodic table. So aluminum is 26.98. And let's see, we have sulfur. Sulfur is 32.07. And oxygen is 16. Wow, don't have a lot of room to work here. All right, so we have aluminum. There are 2 aluminums. Each aluminum is 26.98. What else did we have? We have sulfur. There are 3 sulfurs. Each sulfur, we said, was 32.07. And then we have oxygen. Oxygen, so there are total of 12 here, and each one is 16. So you want to be careful when you put this in your calculator. Make sure you're multiplying everything. You should get an answer of 342.17 grams per mole. Okay, so we have a balanced reaction, and it says calculate the moles of aluminum produced from 2.5 moles of sodium. Okay, so anytime we're working these, we always start with our given number. So we have, let's see, 2.5 moles of sodium, Na. And it's asking us to calculate the moles of aluminum. So we're going from sodium to aluminum. If you look, for every 6 moles of sodium, we're going to get 2 moles of aluminum. So we want our units to be diagonal from each other. So for every 6 moles of sodium, we're going to get 2 moles of aluminum. So 2.5 times 2 over 6 is going to yield 0.83. And our units, so these will cancel with these, our units are going to be 0.83 moles of aluminum. Okay, calculate the grams. All right, this one's going to be a little more complicated. So we start with our given number. Our given number is 3.75 times 10 to the 11th molecules of Al2SO4, and like that. Okay, so we're going to need a couple steps here because it's asking us to find grams of our Na2SO4. So first thing we're going to need to do is convert to moles. We can't go from molecules to grams, molecules of one thing to grams of another. First, we're going to have to convert to moles. Our second step is converting from moles of one thing to moles of another. And then finally, taking those moles, using the molar mass to go to grams. So we're going to need a total of 3 steps here. All right. So step number 1, we need to turn our Al2SO4 into, we're going to need to turn that into moles. Can't think. All right, so I'm going to try to make this a little bigger so it's easier to see. All right, so to go to moles, we're going to need Avogadro's number. So let me see if I can make this just a little smaller. So Avogadro's number is 6.02 times 10 to the 23rd molecules of Al2SO4. Okay. That's how many molecules are in 1 mole of Al2SO4. Okay, so that's our first step. So if you're following along with units, these units will cancel. So now we're in moles of Al2SO4, and it's asking us to go to grams of Na2SO4. All right, so our next step is to take those moles and do a mole ratio. So looking at our question here, there is not a number in front, so that'll be a 1, and then we have a 3 in front of our sodium Na2SO4. So it's going to be 1 mole and then 3 moles. Okay, these units will cancel. And our final step is to use the molar mass to get our grams. So for every 1 mole, and notice my units are diagonal again, for every 1 mole of Na2SO4, I would need to go to my periodic table and look up the masses for each individual piece and then add them together. Just for time here, I'm going to go ahead and give you that. The answer should be 142.05 grams. Okay, so let me just zoom out a tad here. All right, so there's the whole thing. So when we put this in our calculator, it's going to be 3.75 times 10 to the 11th divided by 6.02 times 10 to the 23rd times 3 over 1, or just 3, times 142.05. And we need to be careful because we have 2 significant figures in our question, so our final answer needs to also have 2 sig figs. So it is going to be, oh, I'm sorry, I was looking at the question above. We actually have 3 sig figs. So our answer is going to be 2.65 times 10 to the negative 11 grams of Na2SO4. Okay. C. Calculate the number of atoms of sodium needed to completely react with 15 grams of Al2SO4. Okay, so for this, we are going to start with our given, and I'm going to zoom in just a tad more. So we have some space here to work. So our given number was 15 grams. And it was Al2. Okay, we need to convert to moles. We can't do anything in grams. We need to convert to moles. So let's do that. I would need the molar mass. So I need to look that up just for time. It's 342.17 grams. All right, that's how many grams are in 1 mole. Okay, our next step is a mole ratio. So we're going to go from Al2SO4 to just sodium. So if you go back to the original question, it is a 1:6 ratio. So for every 1 mole of our aluminum sulfate, we have 6 moles of sodium. All right, and then it's asking us for atoms of sodium. So for every 1 mole of sodium, we're going to need to use Avogadro's number, 6.02 times 10 to the 23rd. These are atoms of sodium. So if we put that into our calculator, we get 1.58 times 10 to the 23rd atoms of sodium. All right, moving on. Determine the percentage of oxygen in Pb3PO42. All right, so for this, we need to zoom in because we don't have enough space here. And let's go to a smaller size. All right, so we have lead, which is Pb, and that's totally not what I was trying to do. Okay, so we have lead, which is Pb. We have phosphorus, and we have oxygen. Let me zoom in just a little bit more. Okay, so if you look at the equation, we have 3 leads. Each lead is, we'd have to look up the amount from the periodic table, 207.2 grams. Phosphorus, we have 2 of them. Okay, I'm getting that from the 2 distributing in. So each phosphorus is 30.97. And then oxygen, we have a total of 8. That's 4 times 2. So that's going to give us 8 oxygens. 8, and each one is 16. So when I multiply and add, I get 811.54 grams per mole. Now, to get the percent of oxygen, it's going to be the mass of oxygen over the mass of the whole thing. Okay, so the percent of oxygen is the mass of oxygen over the mass of the whole thing. So Pb3, PO4, 2. So just the oxygen, so that's 8 times 16 is 128. And then our whole compound, when we figured it out, was 811.54. To get that as a percent, we need to also multiply that by 100. So 128 divided by 811.54 times 100, you get 15.8%. All right. Ten says, 10 is an empirical formula. So 10 says, determine the empirical formula of a molecule containing 18.7% lithium, 16.3% carbon, and 65% oxygen. The substance is found to have a molar mass of 221.67 grams per mole. Determine the molecular formula of the compound. Okay, so we're going to need a little bit more space for this. So I am going to go down to a blank page. Maybe. It's thinking. There we go. Nope, not quite. All right, here we go. So it says, let me rewrite our numbers here. So it says we have 18.7% lithium, 16.3% carbon, and 65.0% oxygen. So if it gives you percents like this, I mean, obviously the percents add up to 100, we have to assume the mass is equal to 100 grams. Okay, you have to make that assumption for this to work. All right, now we have, so if it's 18.7%, that'll be 18.7 grams of lithium. Then we will have 16.3 grams of carbon, and then 65.0 grams of oxygen. All right. Now we need to turn these into moles. So lithium's molar mass is 6.94 grams of lithium for every 1 mole of lithium. Carbon, it's 12.01 grams of carbon in 1 mole of carbon. And then finally, oxygen, it's 16 grams of oxygen in every 1 mole of oxygen. Okay, so we get 2.69 moles here, and we get 1.36 moles here, and then we get 4.06 moles here. At this point, we want to divide by the smallest number, which is 1.36. So let's divide each one by 1.36. And we get approximately 2 here. Obviously, we get 1 here, and then we get approximately 3 here. Okay, so we can take those, and now we can write out our empirical formula. Okay, so lithium, our number was 2. Carbon was by itself, it was only a 1. And then oxygen was a 3. Okay. If we go back up to the question, the question says the substance is found to have a molar mass of 221.67. Okay. So the empirical formula, we need to figure out the molar mass of that. So 2 lithiums, 1 carbon, 3 oxygens. The molar mass of the whole compound is 73.89. Okay, now to find the molecular formula, we're going to take the empirical formula, which is the simplest form, and we're going to apply a multiplier. Okay, to find that multiplier, it's going to be the molecular molar mass over the empirical molar mass. So in the question, it told us the molecular molar mass was 221.67. And we just found the molar mass of the empirical, which is 73.89. So we get a number that is, or we get a multiplier of 3. So basically, we take that multiplier and apply it to our empirical formula. So 3 times 2 gives us 6 lithiums. 3 times 1 gives us 3 carbons. 3 times 3 gives us 9 oxygens. Okay, so this right here is our molecular. All right, so we're moving on. We're going to number 16. 16 says calculate the number of grams of KBr, so potassium bromide, needed to prepare 550 milliliters of a 0.67 molar solution. Okay, so for this, you're going to use the molarity equation. The molarity equation is capital M equals moles over liters. Okay, so couple things here. This has to be in liters. 1 liter is equal to 1,000 milliliters. So if it gives you milliliters like it did in the question here, you do need to convert. So I'm going to zoom in here. Okay, so we have 550 milliliters. So that's equal to, so 550 milliliters is equal to 0.55 liters. So if you look at the equation, nowhere in the equation does it give us, it doesn't give us grams anywhere. Okay, we can solve for moles, and then we can turn our moles into grams. So we're going to start with our volume, so 0.55 liters. And we're going to use the molarity as a conversion. So it gave us the molarity of 0.67. So that means that there are 0.67 moles in 1 liter. And then to go from moles to grams, we just need the molar mass. So 1 mole. So to find the molar mass of potassium bromide, we need to look up potassium and bromine, add them together. It's 119 grams. So when you put this in your calculator and multiply, you get an answer of 44 grams. All right. 13 says calculate the molarity of a saturated solution of NaClO3 at 25 degrees based on the solubility chart in problem 15. Okay, so we have this nice solubility chart right here. And NaClO3 is this curve right here. 25 degrees is this spot right here. So we're going to follow 25 degrees up to the curve. And it looks like we can dissolve 110 grams. So it tells us it's saturated. So 110 grams. Remember, if you're on the curve, you're saturated. If you're below the curve, you're unsaturated. So we have 110 grams. We're going to convert that to moles. So we need the molar mass of NaClO3, which is 106.44 grams. That's how many grams are in 1 mole. So we plug that into our calculator. So 110 divided by 106.44, you get an answer of 1.03. And we have 2 sig figs, so our answer would be 1.0 moles. But it's asking us to find molarity. So our molarity would be 1.0 molar. There's 1 mole per liter. Okay, 18 says calculate the percent by mass of sucrose in a solution made by dissolving 7.6 grams of sucrose in 83.4 grams of water. Okay, so sucrose, you would have to find the molar mass of. Oh, wait, no, you don't need the molar mass here. So here it's saying you have dissolved 7.6 grams of sucrose. You're dissolving that in water. That is your solute. Water is your solvent. And the solution is your solute plus your solvent. So to solve this, it's going to be the mass of solute over the mass of the solution times 100. So the solute is our sucrose. So it's going to be 7.6 grams. That's what we're dissolving. And then our solution is the solute plus the solvent. So that's going to be 7.6 plus the 83.4 grams of water. And then we multiply that by 100. So since we have two things in the denominator, I would definitely put those in parentheses when you're putting this in your calculator. So if you carefully enter this in your calculator, you should get an answer of 8.4%. All right, so let's take a look at 19. 19 says, calculate the percent by volume for a solution made from 20 milliliters of methyl alcohol in enough water to give 475 milliliters of solution. So here they're giving us the volume of the solution. The methyl alcohol would be your solvent, your solute. So our percent by volume, it's like the same exact formula. It's the volume of the solute over the volume of your solution times 100. So 20 milliliters of methyl alcohol, that's your solute. And then your solution is 475 milliliters. And then we multiply that by 100. So that would be 4.21%. So anytime it's asking you like percent by volume, percent by mass, it's always the mass or the volume of the part over the whole. The solution is the whole thing. Okay, the last question for this unit is calculate the concentration in parts per million of a solution made with 18.5 grams of salt in 125,000 grams of water. That's how many grams of water you should drink in a day. Actually, I don't know if that's true. All right, so the formula for parts per million, it's the same thing. Mass of solute over the mass of the solution and then we multiply that by, because it's parts per million, we multiply it by a million. That's 6 zeros. My paycheck has that many zeros in it. That's not true. All right. It tells us we have 18.5 grams of salt. And 125,000 grams of water. And then we're going to multiply that by a million. Okay. So when we do that, we get 150. We need 3 sig figs. So I'm just going to add a decimal right there. That now makes that 3 sig figs. And our units for parts per million are ppm, or just parts per million. All right, so that was solution stoich. We're going to move on to kinetics and equilibrium, which is unit 8. So it says use a figure below to answer the following questions. Okay, so let's go ahead and let's label a few things on here. So the left side, these are the reactants. The right side are the products. Okay. What else do we have on here? Let me insert a line here. All right, what's it called when you go from the reactants up to the very top? What would that be? That's EA, that's our activation energy. And the difference in energy between our reactants and our products is called our delta H. And then at the very top, we have our activated complex. Okay. We don't have any numbers on here, so I'm just going to throw some in here. Let's see, how about this can be 10, this will be 50, and let's make this 100. I'm just throwing some numbers on here. We should have had some numbers on our y-axis. I'm just going to throw some numbers on here so we can answer these questions. It says determine the potential energy of the reactants. So I would just go from my reactants over to the y-axis, and the potential energy is 50, and let's say our units are kilojoules here. Determine the potential energy of the products. So again, I would just follow my products over to the y-axis, and the energy is 10. Activation energy is from the reactants to the top of the hill. So the top of the hill is 100, we said. And our reactants are at 50. So the activation energy would be 50 kilojoules in this case. Change in enthalpy, we go from 10 to 50. It's always products minus reactants. So it's going to be 10, which is our products, minus 50, which is our reactants, and we get negative 40. Okay, the negative means that it's exothermic, which is our next question. If it's positive, it's endothermic. Exothermic means that it's losing energy. Endothermic means that it's absorbing energy. So if you look at the graph here, you're ending up with less energy than you started with. The products have less energy than you started with, so that energy was released. If our graph looked like this would be endothermic because I'm ending with more energy than I started with. Label the curve that represents the reaction progress with a catalyst and without a catalyst. Okay. So all a catalyst does is it lowers the activation energy. So this curve right here, the blue one, this would be no catalyst. And the green one here, the energy's been lowered, that would be with catalyst. So we kind of talked about this. G says, what do you notice about the overall energy change of the reaction with the catalyst compared to the overall energy change without, or of the reaction without a catalyst? It just lowers the energy. The overall energy of the reaction we're still starting at 50 and we're ending at 10, but our activation energy is lower. Okay, explain how each of the following impacts the rate of the reaction. Explain why the rate changes based on collision theory. So the first one says the concentration of a solution is changed from 0.5 to 0.25 molar. Okay, so I'm going to try to illustrate this with a picture here. So in order for a reaction to take place, things have to collide with enough energy and the right orientation. So if you think about a classroom, if we've got that many people in there, that's our concentration before. And then if this is after, with more people in the classroom, there's a greater chance of somebody colliding and a reaction taking place. Same thing happens in a reaction. If we lower the concentration, the chances of those molecules striking each other are less and there's less chance. So the rate is going to decrease. As far as temperature goes, temperature makes the molecules move faster. So if you increase the temperature, you're going to increase the kinetic energy. They're moving faster. So with more people moving around, or with people moving around faster, the chances of a collision are greater. And it's going to increase the rate. Okay, particle size. So it says the particle size of a solute in a reaction is altered by crushing a lump sum into a powder. Okay, the more you can expose, more surface area you have exposed, the faster the reaction rate is going to occur faster. Okay, so just think about like if you're trying to dissolve something in a cup. Like if you're making hot chocolate, if you put the whole candy bar in there, it's going to take longer than if you crush that candy bar into smaller pieces. Okay, kind of the same concept here. Okay, so if you are working with smaller pieces, it's going to react faster. All right. So moving on to reaction rates here. It says use a data table below to calculate the average rates for the following chemical equation. The rate of disappearance of hydrogen, H2, over the first 4.32 seconds. So we're looking at hydrogen over the first 4.32 seconds. So we're going to use this data point here and this data point here. And we're going to use time of 0 and time of 4.32. Your formula for rate is change in concentration over change in time. So our concentration goes from 1 to 0.25. So it's always final minus initial. And the same thing with the time. So here you get 0.174. Our concentration's changing per second, so our units are going to be molarity per second, not meters per second. Rate of appearance of HCl. So let me erase this so we don't get confused. Okay. HCl. What's up? So HCl is right here. So we're going from 4.32 and 2.16. Those are going to be the points that we use. Again, change in concentration over change in time. Okay, you get an answer of 0.231 molarity per second. All right, now moving on to KEQ. Okay, KEQ is products over reactants. And on the equation, if you have a coefficient like we do for these two, those become exponents. So our KEQ, our equation, is going to be products. So that's our carbon dioxide. And because we have that 2, the 2 now becomes an exponent. And then our two reactants. We have carbon monoxide. Again, we have a 2, so that becomes an exponent. And then oxygen. Okay, so if it just asks you for the KEQ, if it asks you for the equation, that's all you would do. Here it gives us values to plug in. So it gives us 0.072 moles of carbon monoxide, 0.068 moles of oxygen, and then 0.03 moles of CO2. So we have those values, we just plug them in. So CO2 is 0.030 squared. Carbon monoxide is 0.072 squared. And then oxygen is 0.068. When you are entering this in your calculator, I would use parentheses on the bottom since we have two pieces there. Don't forget to square. And if you're careful about entering this, you should get an answer of 2.6. All right. So moving on to stressing our system here. It says, determine how the following stresses will shift equilibrium. So we had a saying to help us remember here. If you add, it shifts away. If you subtract, it stays. Okay, increasing the temperature. So heat is on the right side of the equation. If you're increasing temperature, you're adding temperature. So it's going to shift away from where the heat is. So it's going to shift to the left. So it's going to shift left here. The next says removing copper ions. If you're removing, it stays. Okay, so copper is here. You're removing those ions, it's going to go, you're subtracting, it's going to go down. So it's going to stay on the right side, so it's going to shift right. Okay, and then finally, increasing the concentration of chlorine. So chlorine is right here. You're adding, it's going to shift away, so it's going to shift to the left. Okay, so this is a titration question, I believe. So it says it takes 38 milliliters of 0.75 molar NaOH solution to completely neutralize 155 milliliters of H2SO4. What is the concentration of the solution? So we have a base, that's our NaOH. We know the volume, we know the molarity. For our acid, we only know the volume. Okay, so that's totally a titration. So the first thing that we're going to do is we need to figure out moles. So we're going to go, or moles of our acid. So we're going to start with the volume that we were given. This does need to be in liters. So divide it by 1,000. Okay, so we're going to start with that. Okay, we're going to use the molarity to get our moles. The molarity is 0.75, so that means in 1 liter of NaOH, we have 0.75 moles. And then we're going from base to acid. So for every 2 moles of base, we have 1 mole of acid. Okay, so we would stop here because we don't know the other piece of the puzzle here. So when you put this in your calculator, you get 0.01425 moles of H2SO4. To get the molarity, you just plug it into the molarity equation. Okay, so we have our moles now. And it gave us a volume earlier. The volume is 155 milliliters, which is 0.155 liters. And when you do the math here, you get 0.092 molar, which is pretty weak. Okay, on question 27, we can cross this off because we didn't talk about buffers this year. Okay, 28 says sulfuric acid dissociates in water according to the following equation. It says determine the Bronsted-Lowry base in the forward reaction and then in the reverse reaction. Okay, we didn't really talk about going both directions with our reactions. We really only talked about going the forward direction. So for the Bronsted-Lowry definition, a base accepts a hydrogen or proton. Okay, so here we went from 2 hydrogens to 1 hydrogen. So the base would be our base accepts hydrogen. So we'd have to go the other way. So this would be our acid because it's donating a hydrogen. Here, we're going from H2O to H3O. So it gained a hydrogen. So our water would be our base. Going in the reverse reaction, so going from the right to the left, which I don't believe we talked about this in class, but going the other way, we go from 1 hydrogen here to 2 hydrogens here. So our HSO4 would be in the reverse reaction, but I don't believe we talked about that. Should not. All right. Fill in the blanks using the following words: partially, completely, greater, and less. So strong acids completely dissociate. Completely dissociate and have a Ka value that is greater than 1. Weak acids only partially dissociate. And have a Ka value that is less than 1. All right. It says below is the diagram for a combustion of ethane according to the following reaction. Would it be, why would a combustion reaction be exothermic? So exothermic reactions give off heat energy. So I would just put maybe that heat is released. If you've ever put your hand over a fire, you can feel the heat. The heat of a reaction, delta H, for this equation is negative 1559.7. Which arrow represents this value? So delta H is the difference between your products and reactants, so that would be number 4. All right, use the potential energy diagram below to determine the potential energy of the reactants. So I just go over and read. It is 50. For the products, I just take it over to the y-axis. It's 100. Change in enthalpy, I do products minus reactants. So 100 minus 50 is 50 kilojoules. All right. Activation energy is like where you're starting to the top of that hill. So EA is this right here. Our activation energy is right here. So it goes up to 250, and we started at 50. So I just need to subtract. Okay. We are ending with more energy than when we started. So this is going to be an endothermic reaction. You can also identify it as endothermic because our delta H value is positive. So a catalyst lowers our activation energy, so a catalyst would do something like this. So it lowers that activation energy. Okay, we talked about catalysts a little bit. So catalyst is going to increase the rate of the reaction. Catalyst, as I said, decreases the activation energy. And the important thing is the overall energy of the reaction does not change when you have a catalyst, so no effect. Okay, so this is like the last couple things that we talked about with thermochemistry. So it says if 50-gram samples of each of the following metals were heated to 100 degrees and placed in a calorimeter, which would cause the greatest increase in the temperature of water? That would be aluminum because it'll hold the most energy. So I'm just going to make a note. It's got the greatest heat capacity. Okay, 34 says a 150-gram sample of metal at 75 degrees Celsius is added to 150 grams of water at 15 degrees Celsius. The contents of the calorimeter come to a final temperature of 18.3 degrees Celsius. The specific heat of water is 4.184 joules over grams degrees Celsius. Calculate the specific heat capacity of the metal, assuming all the heat lost by the metal is gained by the water. Okay, so this is a calorimetry problem. These also require a lot of space, so what I'm going to do is I'm going to just make a new page here. Maybe. There we go. Now it's trying to add like 80 pages because I clicked it too many times. Okay, so going through the question, we want to separate all the information out. What's the metal? What's the water? Okay, so for the metal, if you read the question, our metal had a mass of 150 grams. Our water also had a mass of 150 grams. When we did it in class, we used 100 grams of water. What else do we have? We have the specific heat. Metal, we don't know what it is. That's what we're trying to find. The specific heat of our water is 4.184 joules over grams degrees Celsius. And then we have an initial temperature, a final temperature, and then a change in temperature. All right, the initial temperature of our metal was 75 degrees Celsius. The final temperature was 18.3. The final temperature of our water is also going to be 18.3. And our water was at room temperature is about 15 degrees Celsius. So we subtract final minus initial. So our change in temperature for the metal is negative 56.7 degrees Celsius. It should be negative because it's giving off that heat energy. And then the change in temperature of our water was 3.3 degrees Celsius. So the equation that we use is negative Q of metal equals Q of the water. So the heat lost by the metal is equal to the heat gained by the water. And we expand this equation, so it's going to be mc delta T of the metal equals mc delta T of the water. So we're just going to plug all this into this equation. So the mass of the metal was 150 grams. We don't know what the specific heat was. And then the change in temperature was negative 56.7. I set that equal to the right side. The mass of our water was 150 grams. The specific heat of our water, 4.184. And then the change in temperature of our water was 3.3 degrees Celsius. Okay, so I would do the math on the right side first because those are all numbers. We don't have any variables. On the left side, we're solving for C. You have two negatives, so you should end up with a positive answer. When you do your math here, you should end up with an answer of 0.244 joules over grams degrees Celsius. If you end up with a negative number, you messed up. All right, so we're moving on to question 35. Oh, this is being super slow. All right, here we go. 35 says, calculate the enthalpy entropy and free energy for the reaction below. Okay, we got this data table. I am going to try and squeeze this all on here. Okay, so let me just zoom in a little bit. All right, for entropy, entropy is delta H. Okay, so delta H, it's going to be equal to products minus reactants. So I'm going to go to my data table here, and I'm going to use the values for delta H. All of my pieces here have a coefficient of 1, so I don't need to multiply any of these values. If they were, so like if it was 2 CaO for the middle piece, I would need to multiply that value by 2. But since they're all 1, I'm just pulling those values straight off. So products, so it'll be negative 635.3 plus a negative 393.5 minus negative 1207. And I get 178.2 kilojoules. For delta S, you do the same exact thing, but you're using the delta S values. One quick thing I want to point out while we're looking at the table, your delta H has the units kilojoules per mole. Your delta S, your entropy, is joules per Kelvin per mole. So just make sure that you, when you do your delta S, you need to divide by 1,000 to get the units. So products minus reactants. So it's going to be 39.8 plus 213.7 minus 92.9. So that's going to be 160.6 joules per Kelvin. We need to divide by 1,000 to get our units as kilojoules. So 0.1606 kilojoules per Kelvin. All right, delta G is equal to delta H minus the temperature in Kelvin, and then you multiply that by delta S. So it tells us in the question it's 25 degrees. So we're going to add 273 to that, and we'll get a temperature of 298 Kelvin. Not degrees Kelvin, it's Kelvin. We plug everything in. So delta H is 178.2 kilojoules, 298 Kelvin, and then 0.1606 kilojoules per Kelvin. You multiply that all together and you get 130.3 kilojoules. All right. 39. 39 is a doozy. I'm going to need some more space for this, so I'm going to put this on another page. Okay. So for this, we're given an equation. We're given some parts here, And we want to make sure that we get an equation at the very end that just looks like our given equation here. So we're allowed to multiply things. We're allowed to flip equations. If we multiply it, we multiply the delta H value by that number. If we flip it, we change the sign. So when I'm working these types of problems, I always go with the original equation and I find out where all the pieces are. So for example, we've got H2SO4. It's on the left side. It's in the first equation, but it's on the wrong side. So I need to flip this. And in doing that, I'm going to flip the sign of my delta H. All right. Let's see. SO3 is in the second equation. It's on the right side in both equations, so I don't need to do anything there. H2O, gas, is in the third equation, and it's on the correct side. So all I need to do here is just flip that first equation. So I'm going to go ahead and rewrite everything. Anything that exists on both sides, we can cross off. So looks like O2 gas is on both sides. We can cross that off. H2S is on both sides. We can cross that off. And H2O liquid is on both sides. We can cross that off. And then when I add these together, I'm just left with the original equation. So now what we do is we just add these up. Make sure you change the sign on the first one. You should get a value of 72.5 kilojoules. All right, on the last problem, number 37. Okay. Where did our graph go? Okay, it says, given the following information, calculate the heat and energy required to heat 25 grams of the substance from 75 degrees to 150 degrees. So like looking at the data table, I don't know what's what. So I'm going to just quickly sketch out a graph here. We're heating it, so we know it's going to be a heating curve. So it's going to look something like this. Okay. Our melting point is at 90 degrees. And our boiling point is at 160 degrees. It says we're going from 75 degrees to 150 degrees. So we're going from like here to like here. So we're going to need 3 steps. Step number 1, we're going to raise the temperature as a solid. Step 2, we're going to transition from a solid to a liquid. Step 3, we're going to raise the temperature of our liquid. Okay, so we're going to be using the first equation for the first and third step since we're changing the temperature. So for the first one, it's Q equals mc delta T. We're going to use the C value for solid since we're a solid in that first step. So the mass is 25 grams. The specific heat value as a solid is 3.0 joules over grams degrees Celsius. And we're going from 75 degrees here to 90. Okay, so if you multiply those numbers, you get 1125 joules. Step 2 is a phase change going from solid to liquid. That's going to use the second equation here. There is no temperature change here, so it's just the mass, 25 grams, times delta H fusion, which is 280 joules per gram. And you should get 7,000 joules. All right, the third step, we have one more temperature change. So 25 grams. We're a liquid in this middle phase here, so that's going to be 2.5 joules over grams degrees Celsius. And we're starting at 90 and moving up to, what did we say? 150. So you should get 3750 joules. All you do at this point is you add those three numbers together. And you should get 11,875 joules. That's it. That's the whole study guide.